All right. All right. So, so today's lecture, we're gonna use the BRST formalism that we've defined in the previous lecture. We're gonna use it to show to prove the general structure of divergences at one loop. The proof can be extended to all loops, but by induction. But I will not do that. And by doing so, we're effectively proving renormalizability of gauge theories here at one loop, and in general can be proven at all loops. So you see that this is a very powerful tool. So of course we have some degree of control via the calculation of the superficial degree of divergence of diagrams and endpoint functions. So we have an idea that gauge theories like the ones we're studying should be renormalizable, but to actually prove that was quite hard, and in particularly for the proof of renormalizability of and unitarity of broken so gauge theories with broken symmetry that can be applied to the real world. And for this, Hoft and Veltman got the Nobel Prize. So it's an important story. All right. So in order to use to find the structure of divergences, we have to derive the so-called Lie-Saint-Just identities. So these are two people, Lie and Saint-Just, not three people, as one might guess. And these identities will be proved using the BRST formalism. So the first observation is that the quantum action, that is the classical action plus gauge fixed term plus ghost term, is invariant under BRST transformations. And then so for most theories, in fact, for the gauge theories that we're talking about that make sense at the quantum level, the integration measure is invariant as well. So I've said that when we have gauge invariance, when we have some invariance under some group, not necessarily local, we expect that the action is invariant, but the measure itself could, in principle, have what is called an anomaly. That is, could be not invariant at the loop level, and so that's a possibility that we're gonna treat later on in the course. But since this was a statement about invariance in some group, in particular about gauge invariance, but we've noted that BRST symmetry is the residual global symmetry that appears from gauge symmetry. So in principle, it could be possible to have an anomaly. However, this anomaly itself is what would be called QB exact. The terminology is taken from cohomology theory, where a variation or derivative operator squares to 0. In this case, QB squares to 0, and QB exact means that the anomaly is the variation under the symmetry of something. So so that means that the actual anomaly can be removed by some local finite counterterm, right? So I could, because I mean, we've seen that the quantum action besides the classical term, there's the variation, the Beresford variation of something. So it's QB anti-commuted with a gauge fixing fermion. So that means that we can add a counterterm, a local counterterm, delta S, and then the anomaly itself will be cancelled. All right, so we won't prove this statement in detail. We would need to understand a little bit what how the anomaly arises from the path integral, which takes a little bit of time. So we'll not prove it rigorously here. I just sketched to you why this is so, why we can absorb the BRST transformation, the BRST anomaly into a counter term. So to summarize then, we have both the action and the path integral being invariant modulo this counter term, invariant under BRST. So if we want to calculate some path integral, we want to add some sources for the fields to the action, so that Z depends on J's. And of course, the sources can be defined to be BRST invariant as well. But the field itself are not, which means that when we add terms source times field, so something like G dot A, and also for sources for B and C in the corresponding order, so beta A, C A, so beta is to the left of C because C is always to the right, and BA, gamma A, because BA is always to the left, B is like an eta bar. So the variation of these extra terms that we add in the exponent is equal to just the sources times the variation of the field, right? So since the sources are invariant, the only thing that is not invariant are the fields. So get J dot QB times A, beta A times QB times CA, QB times BA dot gamma A times lambda. So QB times lambda, remember, it's what we understand by the variation delta B. So delta B is understood as QB times lambda. Lambda being the parameter, the infinitesimal parameter. So in order to proceed, we use to derive these Lee's identities. Proceed like in the proof of the word identities. Remember that these are related in spirit with word identities. The word identities comes from gauge invariance, and here we have BRST invariance, which is a global remnant of that. So in order to proceed, then we make a change of variables in the path integral from the original one to the BRST transformed ones. So that's just the trivial redefinition of the variable. So the change leaves the partition function invariant. But if then the effective action is also invariant, so the quantum effective action invariant, then the only thing that is not invariant, as I said, is this. So by so 0 is the variation of redefining the field means adding to A, B, and C, QB A and QB C and QB B. So this is now a new field, and then this is invariant, but this is not invariant. So when I vary the exponent of this, I get the variation itself times the exponent. So then the integral of this variation times E minus S effective plus the source terms, this path integral is 0. So we could continue doing this like we did for word identities, and that's a way. But Lee and Saint-Justin introduced a useful trick, which is useful for gauge theories which are nonlinear. So for electromagnetism, QED, it's not useful since QED is linear in fields. But gauge theory is nonlinear. There are always terms with the gauge field times something else, some other field. And with ghost times ghost. So the trick is to introduce new sources for the parts of the variations that are nonlinear in fields. Now the variation of B is linear in fields, but the variations of A and C are nonlinear in fields. Variation of A gives covariant derivative of C, and the variation of C gives a term with C times C. So these are nonlinear. So the variation of B is linear in fields because it's equal to this. It's -1 over alpha d mu a mu. So the variation of these things are so the variation of A, as I said, is the covariant derivative, which contains the term A mu times C. But the average, meaning the path integral with E minus the effective action plus the sources, the quantum expectation value of this variation is different than the product of quantum of quantum expectation values. So, but we would like to find equations that involve only expectation values. So in order to do that, we have to sort of linearize the variations, and that is why we introduced this trick with adding extra sources, which you can think of as auxiliary fields, for the nonlinear parts of the BRST variations. So I add an extra source term k, with indices mu and a, for the variation of a, with indices mu and a, and I add a source L for the variation of C, with indices A. Variation of A, remember, as I said, is the covariant derivative of C, and the variation of C is FABC, CBCC, with G over 2 in front. All right, so the extra source term, so I get E minus extra source term. So minus S extra source term means I add something to this thing, and for QBC I put a minus in front just for convenience. Oh, and so why is this term invariant? So I said I add something to this, and this was already invariant. I mean, that's why we derived this equation. But now we add an extra term, so that means that we have to, the extra term has to be also invariant, not to change things. But of course, the sources are invariant. That's what sources mean. Sources that are invariant under the BRST. And but there are sources for the variation, for something that's QB of something else. But QB squared is 0. So so acting with QB on QB of something gives 0, right? So that means these extra source terms are BRST invariant as well. Now these extra terms, extra source term K and L, sometimes there is a formalism in which these extra source terms are extended to some object called antifields. In the formalism, antifield formalism. I mean, I will not describe that, but just for you to know, in case you hear the words antifield at some point. In order to see the commutation properties, you note that A is commuting, but QB is anti-commuting. So QB of A is an anti-commuting object. So to get something that's commuting, like the action, means that K is anti-commuting. On the other hand, C is anti-commuting and QB is also anti-commuting. It means QBC is commuting, which means LA is also commuting. Okay. And then, so our equation was this, and we've added these extra terms in the exponent here, which will also invariant. And the trick is, if you remember from the word identities. The point was to write some the things that were not sources. So sources the sources are the things that the path integral is supposed to depend on, and everything else write as a derivative acting on a path integral. Right. So so I write. I have here J dot QBA. Right. QBA, however, to get QBA from the exponent, to get it down from the exponent, I have to take derivative with respect to K. So I have this term added here, K times QBA. So to get QBA down, I have to take derivative with respect to K of this E minus S effective, right? But the derivative doesn't depend on A, B, and C, because it depends only on the source. So it can be taken outside, right? Outside the path integral. So you get in here a term, still integral over x, but the path integral, that is the integral over fields, it's already done, and times the partition function z, which I've rewritten as exponent minus free energy. So this is I'm very bad at writing these things, but this would be z. So derivative of z with respect to k gives me this term QBA times QBA times E minus S effective. All right, and similarly for the other things. So here I have beta times QBC, but QBC, to get it down from the exponent, I have to take derivative with respect to L. And then finally, I have gamma A times variation of B. Now, variation of B is not something, we haven't added a source term for it, but then I have to remember what the variation of respect to A is minus 1 over alpha d mu A mu. So I substitute this. Sorry, I just can't use this pointer. So anyway, I substitute this minus 1 over alpha d mu A mu in here. So I replace QB dA. Well, maybe if I do. Damn it. Anyway, so I get minus 1 over alpha d mu A mu dot Q dot gamma A, right? And then A itself can be gotten down from the exponent by taking the derivative with respect to J. All right, so in this equation, then I get minus 1 over alpha d times the variation with respect to J dot gamma A. All right, and as I said, this is the path integral here that depends on the sources. It's written as E minus the free energy W. But then when I take these derivatives of exponent, is the same as derivative on W times E minus W. But then of course I can peel off E minus W and say that sources times derivatives of W integrated gives 0. So this is this procedure here is the procedure that we've used to derive word identities or Dyson-Schwinger identities, meaning that we have an equation involving derivatives acting on some endpoint function or some free or some endpoint function. The free energy itself is a 0-point function. But like in the case of word identities or Dyson-Schwinger case, it is nicer to continue and make a Legendre transform to the 1pi endpoint function. So this W is a connected 0-point function, but let's make a Legendre transform to the 1pi functions, that is to gamma, to the quantum effective action. So the effective action depends on the classical fields, right? So the Legendre transform is written as W itself, that depends on sources, plus an integral over sources times fields, times classical fields, right? All right. And by looking at this Legendre equation, we find various relations. So I take derivatives with respect to either sources or classical fields. So let me take derivative with respect to A mu classical. Right, then so the derivative of gamma with respect to A mu classical. I should emphasize that K and L are sources, but they come from a mathematical trick, right? From the nonlinear parts. So gamma, even though it's a quantum effective action, so it should depend only on classical fields, not on sources. But K and L are fake sources, right? They're sources that introduced via a trick. So that's why we make the usual Legendre transform over the fields times the sources, but not the nonlinear parts of the fields times sources, because that's well, that doesn't quite make sense in terms of Legendre transform. So gamma itself depends on the fields, plus this fake sources K and L. So taking derivative with respect to all of these objects. So let's take derivative with respect to A mu. With respect to A mu, the free energy doesn't depend, and then the only possibility is in this source time field term. So I get the field, the source. So the variation of the quantum effective action with respect to A mu classical gives J mu. Similarly, with respect to the variation with respect to C gives minus beta. This is minus beta because I vary from the left, and then the variation of the quantum effective action with respect to B again appears only here, and now I vary from the left, so I get plus gamma A. Now variation with respect to K of the quantum effective action. Now this is also the variation of the free energy with respect to K. We don't have this in the Legendre term. A variation with respect to L also of gamma is also the same variation with respect to W of the free energy. Finally, we can also we can also add one more equation. I can value with respect to J mu, which does not appear on the left-hand side. It appears twice in the right-hand side. So variation with respect to W of J plus the variation here is A mu classical is 0. So the variation of W with respect to J is minus A mu classical. I could the reason so I could write also the same equations, the same kind of equation for W and gamma, but it's not useful for us. Anyway, so our equation that we've derived so far was this one. So now I can substitute the variations with respect to W. So variation of K of W is variation of K of gamma. Now J is the variation of gamma with respect to A classical. So the first term is this one. And the second term, W is minus W is the variation of gamma with respect to C classical. The variation of W with respect to L is the variation of gamma with respect to L. So the second term is this one. Finally, third term, variation of W with respect to J is minus A classical. And gamma is the variation of gamma with respect to B. So derivative acts on the variation with respect to W of J. So on A mu classical. So I get D gamma dB classical plus one, so plus the variation of gamma with respect to B classical, 1 over alpha d mu A mu classical. So that's one equation that we've obtained that involves various variations of the quantum effective action. And this was from BRST invariance. But let me derive one more equation that that comes from the invariance of the quantum effective action under a shift of B. Remember that that I had. So one way of writing the Gauss term was partial variation of B times covariant derivation of C. So shifting B, therefore, doesn't do anything. Um, um, so we do the same thing. We like we did in the first equation, namely we redefine variables from variables in the path interval from the original variables, in this case BA, to the transform variables, in this case BA plus some variation. So BA plus some variation is called the new integration variable, BA prime, and I drop the prime. And then in the exponent, I will get the variation of the exponent, but the effective action is invariant. And the source term is well, the extra source term doesn't contain it. So the extra source term was this thing, and doesn't contain B. And so the only thing that appears is the variation of B times the source, and then I can, if I partially integrate the del A onto C, then I can consider the variation of the, so from the Gauss term in the action, I can consider so minus the variation of B times del d mu C. So in other words, the variation of the exponent is minus variation of A times del, and d mu A is QB of A mu, plus gamma A. And this is the variation of an exponent, which when I vary E minus the exponent, I get the variation, I get this variation times E minus exponent. So as before, then 0 is the variation, so the variation of the path integral under this redefinition of variables is 0, and is equal to the path integral times this variation, delta BA times d mu QBA plus gamma A. So this is the variation times E minus the exponent. This is the variation of the exponent times E minus exponent. However, this equation is true for any BA of X. So I can put it to I can peel it off. So I have integral over X delta B of X. So so I can peel off this, and then I'm left with this term inside the path integral. But then I remember that QBA has a source K. So in the exponent here, I have k times QBA. And so I can write QBA as variation with respect to k of the exponent. And then this variation with respect to k, I can take it outside the path integral. So from the first term, I get, as before, I get d mu times variation with respect to k of the path integral, z, which is written now as E minus the partition function. Then plus the second term is already a source, so already that can be taken outside the path integral. So I have d mu variation with respect to k plus gamma a of E minus the free action, the free energy. So this is the second equation. And now I remember also my previous equations. So the variation with respect to k of w was equal to the variation with respect to k of gamma of the quantum effective action, and gamma a was equal to the variation of effective action with respect to b. So I get this equation: del mu variation of gamma with respect to Ka minus variation effective action with respect to B classical is 0. So that's the second equation that we obtain. So the first one was this one, and the second one is this one. And from these two equations, we will derive the Slavnov-Taylor identities that we found sort of experimentally, so to speak, in the one-loop renormalization. We found that they were true at one loop, and now we see that they are actually true at all loops. First of all, the equations are equations for variations of the quantum effective action gamma, but we can simplify a little bit by removing the gauge fixing term from the quantum effective action. So the quantum effective action gamma contains this classical gauge fixing term 1/2 alpha d mu a mu squared. So I define gamma tilde as gamma minus this term. So why this is so? So remember that that the quantum effective action is written as related to a path integral of the path integral of E minus the action, and the action includes the gauge fixing term written like this. But then this is written, so this path integral is equal to E minus the free energy, and the free energy and gamma are related through a Legendre transform. So as you see, that will mean that the quantum effective action will also contain this classical gauge fixing term. So the reason to remove this is that in this equation I have this term that looks a little bit ugly with respect to this, the first two. So d mu, a mu, classical. Now will be absorbed. So when I vary gamma tilde with respect to a mu classical, I would get the variation of gamma with respect to a mu classical minus 1 over alpha d mu a mu classical with one more derivatives. So so I use let me see. So I use this equation to rewrite d gamma dB as del mu del gamma dk. Then path integrate one more derivative to get on this one, and then del gamma del k appears in here, multiplying del gamma del a mu. So as I said, when I vary del gamma tilde with respect to a mu, I get del gamma with respect to del mu. And then from this one, I'll get del mu of 1 over alpha del mu a mu classical. Right? So in the so using the two equations, removing this gauge fixing term means that the first equation is also contains only 2 terms instead of 3. So, and they're both quadratic in gamma tilde. So I get this one equation, and the second equation is linear in gamma tilde. So these two equations, these two final equations, are called the Lie-Saint-Justin identities. All right. So let's now use this Lie-Saint-Justin identities to find the structure of divergences, and also from it, the structure of divergences shows that there's a relation between renormalization factors called these Slavnov-Taylor identities. All right, so first of all, we've added to the action in the path integral, I've added these new source terms. So source term k times variation of a, and minus L times variation of C. Explicitly, then I have k times del CA plus G FABC A mu B CC plus L times G over 2 FABC CBCC. So I have 3 extra terms in the action. So in principle, that means that this introduces 3 extra possible divergent terms. So we will make the analysis, as I said, to all loops, but we'll just analyze that one loop. So at one loop, these three terms in the action implies that there should be three possible divergences, and in fact there are. So let's consider the first term. Oops. Let's consider the first term. Just a moment. So the first term is k mu del mu Ca. So the sources in Feynman diagrams are represented by some circle with a cross on it, which means that field lines end on it. That's what being a source means. So on one side I have K, and this is connected with the field C. So the classical term would be a propagation between C and K. So that's represented by this line. That's a propagator between C, connecting C with K. But at one loop, I can have also a correction with a gauge field connecting the line with K. And why is that? Well, because K has also a line that has also a term. There's also a term with K, C, and the gauge field. That's this second term, K, C, and the gauge field. And of course, there's also a term with two goals, B and C, and the gauge field A. Since the ghost action is B del mu covariant D on C, and covariant D means there includes a gauge field. All right, so we do have such a one term, one loop correction to this classical term. Then I also have this divergence, which has a term K, a C, and a gauge field. Well, this is this second term, right? There's a K, there's a C, and the gauge field. And again, exactly the same thing. Exactly the same thing. The reason this Feynman diagram exists is exactly for the same thing. So I have this KC gauge field interaction, and also have the BC gauge field interaction here and also here. So this Feynman diagram exists, and then I also have a divergence for this corresponding to this last term in the action, LCC. So the source L with a C and another C, and this corrects the classical term LCC with a one loop. And again, the reason is because there's this BCA interaction both here and here. Right, so this Feynman diagram exists and corrects the third classical term, this one. All right, why are they divergent? so well, they're divergent. So basically the reason why this is divergent is because I can replace, so this this K is understood here as a sink or a source of ghost. You can think of it like this because of this first first term. So K produces a ghost. So replace this K with a line, a ghost line. So just this ghost line just extending like this, right? Doing this will not change the expression, the expression for the Feynman diagram. The expression for the Feynman diagram is a loop integral, and then these two vertices, right, and these two propagators. So this Feynman diagram, the expression for this Feynman diagram, is exactly the same as the one with just a ghost line and a gluon line correcting it. So this Feynman diagram we already seen before, that it exists and it's divergent. So since that's divergent, this is also divergent. Now the same comment applies for the second one. This K is again a source for ghosts. So just remove, if you just remove this K and instead continue this ghost line like this, you obtain a one loop correction for the ghost gluon vertex, which you already seen before and already seen that is divergent. So this second term is also divergent. And the third term, again, the same thing. It's just that now L is understood, instead of ghosts, think of it as replacing a gluon line. So so there is a Feynman diagram where I have a gluon line in here, and the ghost in here, and the ghost in here. Right, so this would be ghost gluon, and we've seen that that there is a divergent Feynman diagram like this, with a gluon ghost, and then a gluon line between the two ghost lines. Right. So so this so right, maybe so maybe let's try to see, to write like this. So by replacing the sources with some lines, here it goes lines, here a gluon line, we see that nothing happens to the expression for the Feynman integral, and we do know, we've calculated before, that these corresponding Feynman diagrams are divergent. So we know we've introduced three new divergences. All right. So what have we learned? We've learned that that we have three new divergent terms, so three new renormalization factors Z, and the counter term that we add to gamma tilde, to the quantum effective action, would be Z3 tilde minus 1 times this first classical term, K del C, minus Z1 tilde minus 1 times the second classical term, plus X minus 1, so plus X minus 1 LFCC. Okay. So I've written like this. Otherwise, I should have put minus before. So minus X minus 1 L times G over 2 FCC. Now I've anticipated things a little bit. So Z1 tilde and Z3 tilde are renormalization factors that were used before. These so these were already defined before. So in principle, I should have written, like I wrote here, X. Here I should have written some Y and Z or something like this. Well, or rather Y1 tilde, 1, 2 tilde, or something like this. And then prove that these new renormalization factors are in fact equal to the previously defined renormalization factors Z1 tilde, Z3 tilde. All right. So now, let's use the Lee-Sandrus-Stein identities. These two. We will use these identities, and we would use them at one loop, and we will show that they constrain completely the structure of the identity of the structure of the divergence. So we use it at one loop. That means that I write the effective action as a classical part, gamma 0, and one loop part, h bar, gamma 1. So more precisely, the divergent part of the gamma 1, because we're interested in just the structure of the divergences. And gamma 0, the part is this one. All right, so this is gamma tilde. So I've removed the gauge fixing term by defining gamma tilde. So I have the classical action, the ghost action, and the sources K and L. Now, so from gamma tilde divergent, we note that the d mu times variation of gamma tilde divergent with respect to k is equal to this, right? So there's an extra divergent that acts on d mu c, and an extra divergent that acts on a dot c. But otherwise, what we're looking at is the term with k in gamma tilde divergent, right? Which is this one and this one. And the second Lie-Ajustin identity was del gamma with respect to del b equal to the variation of gamma tilde with respect to b, and this is del variation of gamma tilde with respect to k, which is this. All right. So having obtained this equation, I know that the variation, so I'm concentrating on divergent part. So that means, so here I should be divergent. So integrating this equation, I know now that the variation of the divergent part of gamma tilde with respect to b is this. So I do have a term with b d mu c, and one with b fabc d mu a mu b c. So integrating them, I have this. But gamma tilde depends on a, b, and c. And here and when I have a b, it's always coupled with a c. So I've isolated, I've calculated, so to speak. I've calculated the structure that depends on D, therefore also that depends on C. So what we're left with is just the part that depends on A only. So from the divergent part depending on A, B, C, we reduced to the divergent part that depends on A and plus something known. Okay. Now, we can compare with the one loop definition that we had before, and we can see that we had defined Z3 tilde as the coefficient of the propagator for B and C. So so Z3 tilde was the randomization factor coming from the randomization wave function randomization of B and C. And then I had Z1 tilde randomizing the vertex part of the ghost term. So B del mu times A times C, right? So that was also called, the randomization factor was called Z1 tilde. So you see, we've started with defining. So here I could have, as I said, I could have written here some other y1 tilde and here y2 tilde in the new divergence for these fake sources K and L, and then by using the Slavno-Taylor identities, for using the Lie-Ajustin identities, I found that the randomization factors are actually Z3 tilde and Z1 tilde defined before. Okay. And moreover, I know that there is no other divergent part that depends on B and C. I reduced the divergent part to only the divergent part depending on A. Okay, so now it means we're left with fixing completely the divergent part that depends on A. In order to do that, we look at the first Slavnov-Taylor, first Lee-Zajustan identity, this one, which has two variations, two terms with products of two variations of gamma tilde. And since it's a product of two variations, and I'm interested in equations at one loop, what I'll do is I have one gamma tilde 0 and one gamma tilde 1. That's the variation, that's the first order variation of this product with one gamma tilde and another gamma tilde. So the equation that we get is like this. So I can have either the first gamma tilde be divergent and the second be zero, zeroth order, or either the first order, the first gamma tilde be one loop divergent and the second be classical, or the first be classical and the second be one loop divergent. And that's true both in the first term of the identity or in the second term as well. So now I get an equation involving 4 terms like this. And now I need to solve this. All right. But I already know what the classical term gamma tilde 0 is. So I can just substitute this. Gamma tilde 0 is this. So the divergent part with respect to K and L was reduced to one with A, B, and C, plus these 3 divergent times depending on K and L. So I know what this is, and also I know what this is. And then from this step, I know what this is, what this is, and I know what, what this is. And the only thing I don't know is this. That's what I try to calculate. So this I try to calculate, and then everything else in this equation I know. So now I will try to solve this equation. Okay. So in this equation, I look at terms first at terms that are linear in K. So the first thing to check is so the terms let's see. So the terms coming from these two should cancel. So the variation of gamma tilde with respect to gamma tilde 0 with respect to A is so so I look at the terms linear in K. So terms linear in K, I obtain from this. So if I vary gamma tilde 0 with respect to A and I look at term proportional to K, is given by this, and the variation with respect to QBA is a covariant derivative of C, which contains a term with A times C. So if I vary with respect to A, I get a term K times C. So this K times C. So this is the variation of gamma tilde 0 with respect to A, the term proportional to K. And then from the variation of gamma tilde divergence with respect to K, I'll get Z3 tilde minus 1 del C. Sorry, I get this, and Z tilde minus 1 with respect to this. So all in all, Z tilde. Well, I am a little bit confused because I get these two terms, but yeah, okay, sorry. So well, okay, so I actually didn't write the equation in here for the canceling. I guess I left it for you to check that the terms linear in K for the variation in the second and the third term do cancel. I tried to do it in my head, but I suppose I should have a blackboard to to check that explicitly. But then so those two cancel identically, but we're left then with the contributions from the first term and the fourth term. So the contribution from the fourth term, I can look at variation of gamma 0 with respect to K. Variation of gamma 0 with respect to K is minus the QB on A, which is d mu C. So minus d mu C with a minus in front. And then this is multiplied by the variation of gamma divergence with respect to A. Just a moment, because I don't think I get the right result. All right, so I'm looking at the variation of gamma divergence with respect to A. That's term that's linear in K. So these two again are linear in K, but this does not depend on A. So this is linear in K. I vary with respect to A. I get Z1 tilde minus 1 GFABC times CC. All right, so this is what I get. That's linear in K from this term. And then times this, which as I said is d mu C. And there were two minuses that canceled. And now from the fourth term, the variation of gamma 0 with respect to C. Variation of gamma 0 with respect to C. That's linear in k. So there's this term that's linear in k. So it's minus k times the variation of a mu is covariant derivative of c. But I partially integrate it, so I get plus covariant derivative of k times c, and then varying with respect to c of gamma 0, I get this. Because the variation is from the left, whereas c is on the right, then I get minus. So minus d mu k mu a. Now times the variation of the divergent part with respect to L. Well, the divergent part with respect to L is x minus 1 times minus g over 2 FABC CCC. This. All right. So the equation that we get, so terms linear in K from this, is now I observe that here I also have the same terms, but now multiplied by two different coefficients. So now I do get an equation for the coefficients. I get that x is actually equal to xz1 tilde. So from the from this isolation of the divergent terms depending on B and C, I obtained that that the terms Z1 tilde and Z3 tilde were the ones that were defined before. And now, moreover, I've defined that x in here is equal to Z1 tilde. So the three new divergences that I've added to the theory through these three divergent Feynman diagrams were actually new, not new divergences, were the old divergences that already was clear through the Feynman, to the expression of the Feynman integrals that we found, because Feynman integrals were the same as the, as I said, as the corresponding to the Feynman diagrams with a ghost here, and a gluon here. But moreover, now we've found explicitly that the three new renormalization factors that we added were actually not new, were the old ones. So Z1 tilde and Z1 tilde twice and Z3 tilde. All right, so already we found that acting by adding this fake source terms, we have not modified the theory, we have not added new divergences, there are actually the old divergences. Now, to look at terms in this equation that are linear in A, but don't contain neither K nor L, and moreover are linear in C. So to do this, we think of the divergent part that depends on A as having a quadratic term, a cubic term, and a fourth order term. So since I'm looking at terms linear in A in this equation, if I vary here with respect to A, this will give 1A. So that's what I should do. And then this is multiplied times delta gamma 0 of k0. So I get the quadratic part, the variation of the quadratic part with respect to A, and then multiplied with the variation of gamma 0 with respect to k, which is d mu c. Then from the second term, again varying gamma 0 with respect to A, I get a term linear in A. So that's what I should do. I get covariant derivative of A, the linear part of that. And then the variation of gamma tilde with respect gamma tilde 1 with respect to k is this one, z3 tilde minus 1 d nu c. Remember, we're looking at terms linear in A and linear in C. So here, normally I would have the covariant part, covariant derivative of C, but that contains an extra A, so that I drop. So I look only at d mu c. And then from the last term, the variation of the divergent part with respect to L, that's if you look here, the divergent part with respect to L, that's CC. So that's quadratic in C, so that's not something we're interested in. So that gives 0 with respect to the terms that we're looking at. So we get this equation for the divergent part with respect to A. Its variation with respect to A times d mu c is equal to this. But moreover, this also we're looking at so we're looking at terms linear in A, so I can drop the covariant, is just keep the normal derivative. And moreover, here I look at the linear part in A. So that means the covariant derivative is also dropped. Well, what I'll get is d mu d nu acting on f mu nu. So this is symmetric in mu nu, and f mu nu is, sorry, d mu a nu minus d mu a mu is antisymmetric, so this is 0. So this second term gives 0, right? And this term this third term, as I said, we get a covariant part linear in A, but then the variation with respect to C get so this term will give nothing, and this term also gives nothing. So in the end, what we get is this equation, that if I vary the divergent part with respect the quadratic part of the divergent part with respect to A times d mu c is 0, and I partially integrate d mu onto this, so this is 0. So that means that the quadratic part in A of the divergent part is transverse, right? And that uniquely selects the kinetic term, d mu a nu minus d mu a mu squared. So I define then that divergent to be multiplied by Z3 minus 1. I define its divergence, its divergent normalization factor to be called Z3 minus 1. Then next, I look at terms quadratic in A, but not containing K and L. So now I'm interested in, the reason I look at terms quadratic in A is because I'm interested in the variation in calculating the cubic part in A. So then from this one, from the variation of with respect to A, I will get a contribution with a variation with cubic part with respect to A. That would be quadratic in A. And then that will multiply delta gamma 0 with respect to A to K, which is d mu C. All right. So this is my first term. This is the term that I want to calculate. Then I get the variation of the quadratic term with respect to A times the same. So here I would get the covariant part, covariant derivative on C. But the covariant derivative on C also contains this 1A. So then, so this will multiply this variation of gamma 2 with respect to A, which I've already calculated. So this is a term, it's calculated. And then the other terms are calculated similarly. So variation with respect to K, L with respect to L, and all the other terms are terms that I've calculated before. I will not reproduce it because we don't have the time, but we get these terms proportional with Z1 minus 1 and Z3 minus 1. So what this in the end means, so note that all of the terms are proportional to FABC, A mu B, CC. And moreover, this variation will give d mu a mu b minus d mu a mu b, and that's also the same in all the terms. So the only thing that I get is the sum of all the three divergent terms. So here I get Z1 tilde minus 1 plus Z3 tilde minus 1, and then from this one minus Z3 minus 1. So all in all, Z3 minus Z1 tilde minus Z3 tilde minus 1. So this equation has a common factor d mu c, but d mu c is an arbitrary function, so I can peel off x, And then I can get the equation that this bracket is equal to 0. And now integrate it with respect to A to calculate the third divergent part. So the third divergent part is this term times Z3 plus Z1 tilde plus minus Z3. Sorry. Yeah, this is the typos here. No. Yeah, here. Linear B, linear C. Z3 tilde. Now this is minus, and here minus, like this. So, but you note that the divergent part of the cubic term in the one loop calculation was called Z1. So at one loop, then we get that Z11 is equal to this thing, Z3 no, sorry, this is correct. This is correct, and this is wrong here. The coefficients here are wrong, so here is minus Z3 plus and this is as it is. So the coefficient of the cubic term at one loop was called Z1. So at Z1 at one loop is actually equal to this Z3 at one loop plus Z1 at Z1 tilde at one loop minus Z3 tilde at one loop. So to order, remember that we expand z's as being to 1 plus the one loop part. So this means that this combination is equal to minus 1. To this combination, Z3, Z1 tilde over Z3 tilde minus 1, because this at tree level, this combination is just 1. So I expand each Z3 in terms of 1 plus its one loop contribution, and then I get this. So this is one of the Slavnov-Taylor identities. Then I do the same for the terms cubic in A and not containing K and L. And then, sorry. So from this, to get a term cubic in A, I have to consider the variation of the divergent part that's fourth order, that's quartic in A. So I get the variation of this with respect to A, and then everything else is again known, and I do the same kind of analysis, and then I integrate again. I will get an equation of the same type, integral of variation of gamma tilde 4 with respect to A, plus some combination of z's times something else, namely this. And integrating with respect to A, I get this standard one loop standard classical term with 4 A's, and in front I get this combination of renormalization factors, but the renormalization factor of A4, it's usually called Z4 at one loop. So I get that Z4 at one loop is equal to these combinations, Z3 1 plus Z2 Z1 1 plus minus 2 Z3 tilde 1, which is equal to this again minus 1. So that's another Slavnov-Taylor identities. So we have obtained two Slavnov-Taylor identities. So one is equal to so one is this one loop, and the other one is this one at one loop, or another way of saying it is this is equal to 0 and this is equal to 0. So we see that we obtained from BRST we obtained the Lie-Eisenstein identities, which kind of completely fix the divergent part of the quantum effective action, and moreover, while fixing the divergent part, we have derived the Slavnov-Taylor identities that relate some of the renormalization factors with others. Now to write the renormalization as renormalization of the new terms, we note that the new terms that we added to the action were K times variation of A, which was K times dc covariant derivative, which means normal derivative plus term with AC, and therefore so this term had the renormalization factor of Z3 tilde, as we've seen before, and this term had the renormalization factor of Z1 tilde. Then L, the extra term with L was L times variation of C, which was FCC, and had the renormalization factor of X, which we've seen in fact that was Z1 tilde. So to find the renormalization, we noted that from one loop we've redefined the field A0, ghosts B and C this way, this with Z3, this with Z3 tilde, and the action, the coupling with Z1 over Z3 to the 3/2. So that means that indeed I can rewrite. So if I rewrite if I rewrite the renormalization, so I substitute C with respect to C0, to the renormalized C0, and here I replace G with respect to G0, A with respect to A0, C with respect to C0. If I do that, I get a common factor of square root Z3 tilde. So that means that the whole extra source term is renormalized by square root Z3. And do the same for L. We see that this is renormalized by square root Z3. So that means that the sources must be renormalized with K0 with respect to square root Z3, and L0 with square root Z. K0 with respect to square root Z3 tilde, and L0 with respect to square root Z3. And in so doing, I get the complete relation at one loop between gamma and gamma 0, where all the objects in here are renormalized. The fields A, the ghosts BC, extra sources KL, and G, the coupling, and alpha, the Feynman parameter, they're all renormalized. So that means that finally the gauge theory is one loop renormalizable. We've shown this without calculating explicitly anything. We have shown renormalization, note, simply by using BRST symmetry, nothing else, right? In order to write this with various Z's, I had to actually calculate to see that there were some Feynman diagrams that were divergent and so on, and to find this renormalization. But now we've completely isolated the structure of divergences, including the Slavnov-Taylor identities, which allowed us to completely renormalize the quantum effective action. So this is a very powerful statement, and it's a statement that can be continued to any loops through induction, as I mentioned at the beginning. Though we will not do it here because you see already at one loop I skipped many steps because otherwise the proof would have been too long. I've left many steps for you to check. And of course, one can also include fermions in the analysis, because this gauge theory that I wrote here is not particularly interesting. gauge theory by itself will not will not have any physical application. Well, I suppose it could, but for the most interesting things like the standard model, in particular QCD, what we're interested in is to couple the gauge field with some matter, usually with fermions. So one can also include fermions in the analysis and obtain modified Lie-Saint-Justin identities. And so the Lie-Saint-Justin identities with fermions, I left it as an exercise. Also the proof of the Snavlov-Taylor identities. So this is everything that I wanted you to tell you today. All right. So, do you have any questions? Can anybody check that you can still hear me? So.
Yes.
All right. So that means that you don't have any questions. All right. So I'll talk to you next Tuesday at 10. Right. Bye.